Hi, I'm Ellie Pinchers, an Education Officer here at the Royal Meteorological Society. In this series of short films, we're going to be covering some of the background information that teachers may find useful if they're teaching weather and climate at secondary level, and specifically if they're using our weather and climate teaching guide with accompanying classroom resources which can be found on our website MetLink, with links in the text below. In this film, I'm going to be looking at pressure and wind and the relationship between the two. Surface pressure is simply a measure of how much air is above the ground at a given time. At another level in the atmosphere, the air pressure is the measure of how much air is above that level, so air pressure falls with altitude. Air pressure is measured in hectopascals or millibars, which are equivalent, so 1 hectopascal is the same as 1 millibar. Lines of equal pressure are called isobars. Winds are named from the direction they blow from and tend to follow these isobars. In general, surface pressure values are higher in the summer than in the winter, but vary between 950 hectopascals and 1050 hectopascals. A local pressure is labelled high if it's higher than the surrounding pressure, and a local pressure is labelled low if it's lower than the surrounding pressure. There's no absolute value, for example 1000 hectopascals, which differentiates between high and low pressure. If the pressure is less, it simply means that there is less air in the column above that point. In this figure, the shading indicates the pressure falling with height. If you were to go up in a balloon, there would be less air left above your head, and so the pressure is lower. There are various places in the Earth's atmosphere where the air is rising. For example, the larger scale areas associated with the Hadley cell, or smaller scale areas associated with low pressure weather systems like depressions and tropical cyclones, or really small scale areas associated with localised convection like summer thunderstorms or land and sea breezes. The tropopause, which is the boundary between the troposphere, which holds all our weather, and the stratosphere above, at about 10 kilometres, acts as a lid to vertical motion. So air spreads out horizontally or diverges at this level. You can see this sometimes in the shape of a thundercloud. Near the surface, air converges into the column to replace the air being lost through the rising motion. However, this converging air is slowed down by friction at the ground. If more air diverges in the upper levels than converges at the surface, we end up with less air in the column and the pressure falls. This means that we end up with some places that have less air or low pressure and other places where the pressure is high. This is a bit like having 2 buckets of water. If one bucket has more water in than the other, then the barrier between the two is removed. What will happen? The water will rapidly flow to even out the water level. The higher pressure in the bucket with more water pushes the surplus water to the bucket with lower water pressure. Exactly the same happens with the air. If the pressure is higher in one place than the other, then the air will be pushed to where the pressure is lower, and this is called wind. The bigger the pressure difference, the faster the wind blows, or the closer the pressure contours or isobars are to one another, the faster the wind. This is a bit like the contours on an Ordnance Survey map. The closer they are together, the steeper the hill, and the faster a ball would roll down the hill. So the absolute value of pressure in the centre of the depression is less important than the pressure difference between the centre and the edges of the system. This can be seen on this weather map. Where the isobars are closest together, for example the area circled in red, indicating a bigger difference in pressure over a given distance, the wind speed will be fastest. You can very roughly approximate the wind speed by counting the isobars crossing the UK and multiplying by 5 kilometres an hour to give you the surface wind. More accurately, you can use the geostrophic wind scale given at the top of the map. To find the wind speed at a given place, first of all see what latitude you're at. The curved lines of latitude are labelled at 10-degree intervals. Then measure the shortest distance between the contours at this point. In this example, at 60 degrees north, the distance is shown in red. Now measure the same distance from the left-hand side of the scale at the appropriate latitude. Again, this is shown in red. You can then use the curved lines to read the wind speed. Here, the same length red line takes you to somewhere between 50 and 25 knot lines. So the wind speed at the marked place is about 20 knots. The actual wind speed at the ground will always be less than the geostrophic wind because of friction. Friction will slow down the wind more over land than over water. The rule of thumb suggests that the wind will be 2/3 of the geostrophic wind speed over water and 1/3 over land, but it will vary considerably. However, we live on a rotating spherical planet, so we also need to take into account the Coriolis effect, created by the rotation of the Earth. At the simplest level, the Coriolis effect deflects everything moving in the northern hemisphere to the right of its direction of motion, and everything in the southern hemisphere to the left. Put another way, in the northern hemisphere, if you stand with your back to the wind, then the low pressure will be on your left. The Coriolis effect is very easy to demonstrate, and there are plenty of demonstrations and films around, but a lot harder to explain. At a simple level, think about a person standing at the equator. In the course of a day, the planet rotates once, meaning that you've travelled a colossal 2 pi r, where r is the radius of the Earth, so around 6,370 kilometres. That means you travel 40,000 kilometres through space at a speed of about 1,700 kilometres an hour. You don't notice that you're travelling so fast because the air around you is travelling at the same speed, so there's no wind. On the other hand, if you're standing at the pole, all you do in the course of a day is turn around on the spot. You have no speed through space, and similarly the air around you is stationary. Now think about really fast moving tropical air which is being pulled towards the poles by a pressure gradient. As it travels polewards, it moves over the ground which is rotating much slower, and so it overtakes the ground and looks like it's moving from west to east. Similarly, slow moving polar air will be left behind by the rotating Earth and look like it's moving from east to west as it's pulled equatorward by a pressure difference. It turns out that whichever direction the air is moving in, it's diverted by the Coriolis effect. It is simply the result of observing the atmosphere from a surface of a rotating spherical planet. The Earth's axis of rotation is in the same direction as the local vertical at the North Pole, but at 90 degrees to it at the equator. As the air blows from high to low pressure, the Coriolis force acts on it, diverting it, and we end up with air following the pressure contours and blowing around low pressure in an anti-clockwise direction and around high pressure in a clockwise direction in the northern hemisphere. In this schematic representation of the flow around a low pressure area, the black arrows show the direction the air is moving in. The pressure difference pulls the air into the low. This is shown in the blue arrow. The Coriolis force pulls the air to the right of the direction of motion, and that's shown by the red arrows. The two forces are in balance when the air flows in an anti-clockwise direction around the low. In the northern hemisphere, this means the air blows around a low pressure in an anti-clockwise direction and around a high pressure in a clockwise direction, generally following the isobars rather than blowing across them. So unlike a ball rolling down a hill in the analogy, the ball is actually rolling around the hill. So let's look at another weather chart. We know that the wind is following the isobars across the map. To work out which way, you simply need to consider the pressure systems, remembering that wind blows around a low in an anti-clockwise direction and a high in a clockwise direction. It should be possible to put arrows on the isobars, like this, which comply with those rules everywhere on the map. Note that some tiny pressure features may only cause a dent in a pressure contour rather than actually causing rotation around them. The wind follows the pressure contours, continuously changing direction as diverted by each pressure system. Near the ground, friction slows air down a bit, so in practice the wind does actually blow ever so slightly towards the centre of a depression. We name the winds by the direction they are blowing from and not to, so a northerly wind blows from the north to the south. It's worth pointing out that the Coriolis effect varies with latitude and is negligible near the equator, which is why there are no tropical cyclones within 5 degrees latitude of the equator, and that it is a planetary scale effect. It would only have an impact on a small scale motion, such as water draining down a plug hole, under very, very controlled lab conditions. Simple weather apps, typically those embedded in cheap weather stations and smartwatches, use pressure as an indication of when it will rain. When the pressure falls, the rain symbol appears. But there are many causes of rain, which we will look at in the next video. of which only frontal rain is associated with low pressure systems. For many places in the UK, the prevailing wind direction or air mass, which we went through in the previous video, is much more significant. There are a number of good videos that you can access online explaining and demonstrating the Coriolis effect. Links can be found in the text below. Earth.Null School is also a great place to look at the pressure and winds across the globe, in particular for observing the opposite directions of rotation around high and low pressure systems in the northern and southern hemispheres. In the next video, we'll be looking at water in the atmosphere.